let's have a look at theorem 4.4. If A is an n by n matrix, then for any row in A, the determinant of A is equal to the sum along that row of each entry in the ith row times the determinant of the minor with the appropriate negative ones in front. Okay, so let's think about the proof of this. Well, if I equals 1, then this is the easiest proof ever because this is just the definition of derivative. Think about that. If that's a 1 and you're going across the first row, that's actually how we define it. For a fixed I greater than 1, let's write row I as the sum of aij times the standard vectors, right? So the first standard vector would be 1, 0, 0, 0, 0, 0, then 0, 1, 0, 0, 0, 0, 0. And so if you add all of these up, that's going to be the ith row, right? So for any j between 1 and n, let's let bj denote the matrix obtained by replacing row I of A with EJ. Notice these BJs are exactly the things that the lemma in this section applies to, right? Okay. And by theorem 4.3, remember that was the one that said that determinants are linear in each row. The determinant of A is equal to the sum, j equals 1 to n, of A, ij, determinant of bj. So it's linear in that row. I wrote that row like that, so I can just sort of break it apart. And now I have to just calculate these determinants. And by the lemma, ironically, lemmas aren't that important, so they don't number their lemmas. This equals the sum j equals 1 to n of A, ij, negative 1 to the I plus j, right? This, by the lemma, is equal to that. Determinant, now think about it, I've just omitted the jth row and the ith row and the jth entry, so that's the ij minor of that is also the ij minor of A, right? Well, but that was the proof, that was the result we were trying to get to, okay? And this is a nice theorem in its own right, but this is particularly nice because if you think about it the right way, if any matrix has two identical rows, then the determinant is 0. So this is probably requires more proof than your typical corollary. It's actually a proof by induction. Think about this. If n equals 2, the determinant of AB is equal to, right, AB minus AB, which is 0. So hopefully that's pretty obvious. Now, assume it's true for n minus 1, and that A is an n by n matrix, okay? Let I be a row other than the two identical rows. I think this is the interesting part of this proof. Okay, let's think about a matrix that has at least 3 rows. Let's think about an expansion along a row that isn't one of the two identical rows by theorem 4.4. Well, we can just expand along row I, right? Determinant of A equals the sum -1 I plus j to the I plus j, aij, the determinant of A tilde ij. But think about it, what's this? This is a matrix of size n-1 by n-1, and it still has 2 identical rows. But by assumption, the determinant of aij equals 0 for all I and j, since each still has 2 identical rows. Therefore, true by induction. Okay, so there you have it.